Hello, this video is entitled Improper Integrals. Now let's talk about what determines how an integral, why an integral is improper. The basic definition for a definite integral from a to b of f of x dx is that the function f of x must be continuous on the closed interval a to b. So if that's not true, based on one of the following two reasons, it's considered an improper integral if there happens to be some discontinuity in the interval a to b, meaning at either endpoint or somewhere between the two endpoints. And then now this would be probably a little more obvious if it had contained negative infinity or infinity. Now that's not something you would have likely seen in Cal 1, but definite, obviously definite integrals with real number of values you certainly would have seen. Now let's take a look at this example. Negative 2 to 3 of 1 over x squared dx. Now what's kind of interesting about this problem is that if you work this out manually and took the antiderivative and plugged the limits of integration in, you would come up with an answer. Unfortunately, that answer is wrong because it's wrong to evaluate that integral to begin with in a normal fundamental theorem of calculus way. Because in the interval from negative 2 to 3, we have a discontinuity at x equals 0. So therefore, that's what would dictate an improper integral. Now, sometimes these will have answers. This one does not. This one just produces infinity. But sometimes they will still have answers, except we will use the terminology of converging. And there, that's the Maple software. Now, here's what it would look like in a calculator. So you see, it's obviously, that's the older way. Now this way shows it too. But as you can see, it's not reaching any kind of answer. Now here's some more improper integrals. Now obviously the first two are visually easy to see because, like I said, if they've got either infinity in there, it's improper. Now the bottom two have discontinuities. The red arrows I have pointing down here are where the discontinuities occur. The example I showed you a minute ago, the discontinuity was in the interval. Here it's at an endpoint. So you see 0 would make that 3 divided by 0. And then for this one, if you put 4 in there, you'd have 16 minus 16, which is 0, square root of 0, which is 0, in the denominator. Now let's take a look at this one. We're going to see how to work problems like this in just a second. But just to show you, I put this one in Maple, so like I was saying a minute ago, improper integrals, can have answers. They can converge to real number answers. So this one's actually 3 pi over 4. And then like the other page, other example, when they go to infinity, they diverge. Okay, so let's see what we have here. These definitions. Now to manually write out an improper integral correctly by hand, you have to kind of convert it to a limit, because theoretically you can't plug infinity into something because it's a concept more than anything else. You can't plug it in directly for x. But if you replace infinity with some letter, now the choice of letter here doesn't have to be b. Just don't use x, obviously. Use something else, but it's not wrong. I mean, if you don't use, you could use c or something or whatever. But we're going to see c being used in the other example type of problems here shortly. But so this is written as the limit as b goes to infinity, and then so that's how you can, you can't really plug in infinity, but you can use the concept of limits to express approaching towards infinity. So here it's telling me this is only true if f is continuous from a to infinity. Well, you don't have a discontinuity in the intervals anywhere. So now here's the next one. Anytime you have negative infinity, you have to put negative infinity on the lower limit because nothing's smaller than that. And they're just using a different letter a. So like I was saying a minute ago, it's not mathematically wrong, like if you used B here and you used A here, because, you know, the value is going to be whatever the value is. It's not going to be a letter, and then you're replacing the infinity with some sort of letter. So obviously, B is actually going to be some sort of number, but you could use B again right here, and then your function's continuous on negative infinity to B. Now, suppose it went like from this, negative infinity to infinity. You have to break it up as two different integrals added together. You would go negative infinity to some value C, and then from C to infinity, provided that the function is continuous on the real number line. Now, most people for this value of C would use 0, but maybe there might be some instance where somebody might not want to. But I don't want to just say 0 there because that would be wrong. Technically, it could be any real number. But I would do it as negative infinity to 0, and then 0 to infinity, and then add the two results together if they converge. So now we're using using the concept of converge and diverge, which you'll see this a lot in the chapter on sequences and series coming up shortly. So this terminology you'll get used to, because infinity is a concept. When you're approaching infinity, you're not really reaching infinity. So whenever we do come up with an answer, the correct way to say it is that we say it converges to that answer. Now, Maple didn't program their software to do that, but if you look back up here, this example right here where it's 3 pi over 4, technically the answer really is converges to 3 pi over 4. So in other words, but it's so close, but Maple just left out the wording converges to. It's not an exact answer, in other words, but it's infinitely close to being an exact answer. So. And then if the limit, when you evaluate this, it's all going to be about this limit right here, the part that has the limit. If that limit converges, then it's going to be fine. Otherwise, it'll converge to some value. And then otherwise, if it doesn't, you just say diverges. You don't have to specify anything about negative infinity or positive infinity. There's no need to say diverges to negative infinity or diverges to positive infinity. That's not necessary. So that first example up here, let me scroll up for a second. This one that produced infinity right here, we would say that improper integral diverges. That's all you would have to say. Now on handwritten tests, I certainly make sure students, you have to show your work. You can't just write down diverges as an answer and hope it's right. I mean, I would give a student more partial credit in a problem on a handwritten problem if they even got the wrong answer but showed proper work. So now this one, we're going to see how to work these out. This is a special type of improper integral. I don't think you have to necessarily worry about this too much because you could always work these out if you needed to. But it's an interesting theorem and it's accurate. So this says if you're going from 1 to infinity, and you've got dx over x to some positive power on the bottom. So like dx over x squared or dx over x to the fifth. P has to be, well, I guess it doesn't have to be positive, but to really have any relevant meaning in this concept, it needs to be, because why write dx over x to the negative 2 when you can just call it x squared dx? So this is technically true, but I would expect the P to be positive. So this tells using this theorem, you wouldn't have to work it out, because if this P right here is an exponent greater than 1, the improper integral will converge, and it will converge to a value of 1 over P minus 1. If that P is less than or equal to 1, so even just x itself would satisfy this, you have diverges. Let's take a look at these two examples real quick. Okay, we got 1 to infinity. We have x to the 4th. Now, obviously, any multiple here, like this 6, you do include that as part of the answer. It's still, and it's still multiplied by 6. So the P is 4. So it's by definition, it's 1 over 4 minus 1. but because we have the 6 there, it's 6 over 4 minus 1. So it's 6 over 3. That means this integral will converge to 2. And you can see I put that in maple and got 2. And this one, the exponent is x to the 1/4. 1/4 is less than 1. So you have diverges. So automatically it diverges. And the fact that the calculator Maple software spit out infinity, that just backs that up even more that it's diverges. Let's see how we work these out. Now here's the one, 6 over x to the 4th. So what I would do is, I would rewrite this by putting the limit there. Limit is b goes to infinity, and then I replace the infinity with b, like so. So it's all about whether this limit exists. Now what I did is bring the 6 out, and then bring this up for integration purposes. Make that x, I didn't show that step, but x to the -4 came up, and then use the power rule. So it's x to the -3 over -3. So of course 6 divided by -3 is -2. And then now I just rewrote x to the -3 as 1 over x cubed. So you only have to write the limit part wherever the value b is. So when I plug this in other words, so to evaluate this definite integral, I plug the b in for x cubed. So I have limit as b goes to infinity of 1 over b cubed. So what I was just saying here, when you plug the 1 in here, you don't have to use the limit, because it's going to be a constant. And remember, the limit of a constant is always a constant. So you just plug the 1 in there, and you got 1 over 1 cubed, and that's 1. So we don't need the limit written right here. So now the million-dollar question is, if the limit converges, we're going to get a converging improper integral, some value. If it blows up, then the whole thing would just diverge. This one does not blow up, because the limit as b goes to infinity of 1 over b cubed would be 0. So you have -2 times 0 minus 1, which is -2 times -1 converges to 2, which is exactly what we got on the other page using that theorem. And then if you wanted, just for practice, if you wanted to try the second one here, you would see that this limit right here goes to infinity. And that will make it diverge, because you won't have the b on the bottom. The b will end up being on top, and that will make it diverge. Now, for the problems that I like to use for tests and whatnot, I don't like to get these to be too out of hand. In other words, I'm not looking for you to have to use any of the advanced techniques that we've learned in this chapter. In other words, you're going to already have test questions on partial fractions, integration, trig substitution, trig integration. You're already going to have those questions. So I don't want to be redundant and make these too complicated. Maybe a simple integration by parts at the worst, but I generally use U-substitution problems, and then maybe things that lead to like arctan and arcsine, things like that. Now this one, let's take a look at this example. So I rewrote it. The limit as b goes to infinity. I put the b in for the infinity. And this might look like integration by parts, but it is not integration by parts. It would be if it was just natural log of x by itself, but it's not. Because if you let u be ln of x, the du of that is 1 over x dx. And that gives you your x on the bottom right there. So that x on the bottom, so in other words, 1 over x dx, that is du. Now I like changing my limits of integration. Be careful if you don't do that, because I see people that don't do it and they forget to change back to the original variable. That way I don't have to go back to my original variable anymore. I can stay with u. So u of b, putting it there would just be ln of b. You plug 1 in there, natural log of 1 is 0, so u of 1 will be 0. So that means I can write this as the limit as b goes to infinity of 0 to ln of b, and now you just have u du. That's the new integral. So easy. Power rule. That's going to give you 1/2 u squared. Put in ln of b, put in 0. Now remember, for the 0, all we have to do is just plug the 0 in. That's going to be 0, but now we plug in the ln of b for the u. So we have limit as b goes to infinity of ln of b, all quantity squared. Well, long story short, as soon as you plug that in there, that's going to be infinity. I mean, yes, natural log, moves slowly towards infinity, but it goes to infinity. As we've seen before in other sections, the L'Hopital's rule, I believe that was covered, but yeah, it goes to infinity, so game over, diverges. And I put this, I guess, because I didn't have enough space, but I make this a little bigger maybe. Unless I do this. Okay, I paused the video for a moment to kind of rearrange this a little bit. In fact, I might drop this down one more line. I want to make the maple output over there to the right be a little bit larger. So, well, anyway, so you see maple got infinity, so that backs up my diverge answer. All right, so let's take a look at this next example. Which is integration by parts. So, just a quick refresher. Like I said, I don't think I would put an improper integral like this on an exam, but heck, this exam does contain integration by parts. So I think it's interesting to take a look at this. So you still need to know integration by parts. So not totally wasting your time by any means by showing you this. Because I don't like these integrals to be too long and complicated, because we have so much of this notation to keep up with. Those more complicated integrals we've studied were generally, I usually pretty much use just indefinite integrals, without the limits of integration and tracking down all these constants and keeping track of all that, and then the limit notation. That gets pretty messy with these problems. So. All right, I use the tabular method for parts here. You could do this manually if you wanted to. So I'll let u be x, and then dv is e to the negative raised to the negative x over 3. So you take the derivative, that goes to 1, so you're done right there. So in the sign chart, it goes plus, minus, it alternates. And then here, take the antiderivative. Now for e, it's real easy. This one's usually don't have them with fractional exponents, so it might be a little tricky. But and I see I wrote it down here in green. Yes, this is good. I got it written right there so you can see it. But without having to work this out by substitution, which is a complete waste of your time, if you just know that the antiderivative of e to the ax is 1 over a, e to the ax, that'll save you a lot of time and hassle. So every time you're taking an antiderivative of an e term, basically, you are multiplying by 1 over whatever the exponent is. Or you can just say that you're dividing it by the exponent. Okay, so the exponent here is negative 1/3. So 1 divided by negative 1/3 is actually negative 3. So now the pattern would go, you would just start multiplying it then by, you're going to get a new negative 3 every time. So it would go from this to negative 3 to 9. A lot of these problems you're used to them being fractional, because let's say if we had e to the 4x, the next one would be 1/4 e to the 4x. The next one would be 1/16 e to the 4x. This is kind of a rare one here to have a fractional exponent, but this is correct. So you see we carry the lines together like that. And this problem also has a L'Hopital's rule too, so it's kind of serves a couple of purposes from this chapter. Or depending on whatever textbook I'm using at the time in the future in this video, L'Hopital's rule might be studied earlier in the course, which some books are starting to go to that now, but I still have it with these, keeping it with the integration technique section. But it is possible some point in time that it may be earlier. But anyway, it's going to be covered sometime. So we just have, integration by parts. I didn't post the formula there, but it's uv minus v du. And so well, actually, what am I saying? We're using tabular method. So you connect the x with this term right here. It gives you negative 3x e to the negative x over 3. And don't forget the minus right here with that sign. So it becomes 1 times this. So it's minus 9x e to the negative x over 3. So now I'm going to split these up as two pieces, which we can do. So it's the limit of the first one. So what I did is this top, well, actually, no, I didn't. I'm sorry, I did not split it up. I left them together, excuse me. So at this point, I'm plugging the b in to both of those. I could have split them up, though, but I did not. So I had to correct myself there. And this one, so we plug b in here, you get infinity, and e to the negative b over 3 would be the same thing as 1 over e to the b over 3. So that's going to be, when infinity goes in that, that's going to be 0. But we've learned that infinity times 0 is an indeterminate form. You know, it's not always 0. Sometimes it ends up to be other things. You could check some of the L'Hopital's rules problem we did, and I'm certain that we did some where infinity times 0 did not equal 1. So what I did down here below was I just used L'Hopital's rule kind of off to the side, right below it here. So I dropped the e part down, and that's what you do. You pick one of them to drop. So obviously the e was the easiest one to drop. And then you take the derivative of the top and bottom using L'Hopital's rule. And then now you end up with this, and then that clearly goes to 0 even with the negative 3 in front of it. So obviously negative 3 times 0 is 0. So it does end up being 0, but not because it was 0 times infinity. Now this one is 0 strictly because, like I was saying, that the limit of this term by itself is going to go to 0. So that's just 0. So this all zeros out. Now when you plug 0 into this part, you'll get 0. When I put 0 into here, e to the 0 is 1. So it's 9 times 1 is 9. So I have 0 minus 9. So basically I have 0 minus the negative 9. So I get 9. Oh, there I have it written down here, right there. So it converges to 9. And Maple says it converges to 9. So that's good news. Excellent. Now here's let's take a look at this particular one here. Like I say, I like to use arctan problems. These are good. Let's see what we have here. 3 over 4 plus x squared. So we write this as limit as b goes to infinity from 0 to b. And there really isn't a lot of work on this integral. It's just recognizing that it is arctan. It's already, you don't have to do any kind of substitution or anything. It's I didn't have the arctan formula here, but obviously you probably have it somewhere. It's 1 over a arctan of u over a. And u would be x, a would be 2. And there's no du to adjust for, since du would be dx. So I have 1/2, of course we have the 3 that's there, 1/2 tan inverse of x over 2. And so it's going to be 3/2. Limit of b goes to infinity of tan inverse of b over 2. And then when you put 0 in there, tan inverse of 0 is 0. Now the interesting part right here. And I believe this was talked about way back in the section on inverse trig functions in general. And I'm sure it came up probably also again, I think, in L'Hopital's rule. Maybe it didn't, but I think it did. Well, anyway, long story short, tan inverse of infinity, as you're approaching infinity, is actually approaching 90 degrees, which in radian form, of course, is pi over 2. So the tan inverse of infinity has an answer, and it's pi over 2. Now, just if you, let's say you forgot that and go, yeah, I remember that tan inverse of infinity equaled something, but I couldn't remember what it was. Well, you can use your calculator. And make sure you're in degree mode, because you can always change it to radian, but obviously degree mode, like pi over 2, you know, you're looking for weird decimal answers in the calculator. It's easier to look at a degree and then change it to radian. So I just put a giant number in there in degree mode, tan inverse of 9999999, and look what the degree mode is, 89.999. Okay, that tells you 90 degrees. So therefore it tells you it's pi over 2. And then when it's negative infinity, it makes it negative pi over 2. And here I'm just showing that tan inverse of 0 equals 0 that I said right there. All right, so that's the key. Tan inverse of infinity goes to pi over 2. So now we have 3/2 times pi over 2 converges to 3 pi over 4. Oh, that was the one that was on the earlier pages. So I reworked that same example that was on the one. So that one was already done in Maple on another page. If you want to go look at it. Now here's one with negative infinity. It's going to be another arctan. See, okay, I used A here just to kind of follow the way they did it via the definition. But as I said before, now at least in my class it wouldn't matter, but you could use B there also. Like I was saying, it doesn't really matter because one of them is going to be a number. So I'm just following that syntax, but there is nothing wrong with saying B goes to negative infinity and putting B right down there. That would not hurt a thing. So pretty easy arctan. So A is 4, U is X. So it's 3 times 1 over 4, arctan of X over 4. 0 to A. So the 0 goes in there. It's just going to be 0. So we only need the limit for the part when we're plugging the A in. And there's a slight mistake here in the notes, which I'll fix real quick here. That should have said, once I made this step, that should be an A right there, not an X. See if I can freehand draw this properly. I'm not writing on a tablet, I'm using a mouse here, so I mean a mouse pad actually. And that's pretty terrible, but maybe I'll give it one more quick shot here. Perhaps I could maybe let me snag this little thing right here. Sometimes it'll let me grab individual things like that, sometimes it won't. Well, there we go. And I'll put that in there, so I don't have to try to do a terrible job of drawing it again. So that was a mistake. So that should have been A over 4. More like a notation mistake. I didn't totally butcher the problem. But anyway, so A over infinity over 4, negative infinity over 4, still negative infinity. So like I said, arctan of negative infinity is negative pi over 2. So we have 3/4 times 0 minus a minus pi over 2. And that would be 3 pi over 8. There it is right down there. So it converges to 3 pi over 8. So that was exciting. Let's see what else we have down here. We should be ready pretty soon to be moving on to the next type where you have the discontinuities. I'm not going to rework this one, but we did half of it already. We've done the first half. But this one, so see, like I was saying earlier, negative infinity to infinity, I would split it up at 0 and do 2 of them added together. And actually the one we just did was 3 pi over 8. So is the other one. If you did this one, you'll get 3 pi over 8. So together they add up together to be 3 pi over 4 or 3/4 pi. All right. And I guess because I graphed it and that doesn't mean anything. Don't worry about that at all. But because it's symmetrical about the origin like that, that's sort of showing why they're kind of the same areas there. You know, this graph never actually touches the x-axis. That's why you sort of say converges to, because it's not really, when it's finding the area, it's not finding, the exact area. But that's okay. That's not important. Improper integrals with infinite discontinuities. Now this one's a little tricky from a notation standpoint. When you write these out, these have to be, written correctly. And it's possible you could have a question, even a multiple choice format type question, where it just says, set it up properly and pick the right setup, and you would have to know whether this upper thing is a minus or a plus. So if you saw 2 answers that looked exactly the same, except one had the minus and one had the plus, you would have to know which one was which. and why. So this one is saying we're on the interval closed at A, open at B. So we're going from A to B. So that's saying the discontinuity is at B. And here's what I was mentioning earlier. Now they're using letter C here. So because we're only approaching this one direction, that's why this has to be written as a one-sided limit to be proper. Infinities, even though you are only approaching them from one direction, you don't have to worry about plus and minus because they're not really real values. Like, for example, if you're approaching positive infinity, you can't come from it two directions anyway. But if you're approaching a number, let's say like 2, you can actually approach it from two different directions. So that's why we have this notation to indicate which direction. Well, I'm showing you that the discontinuities between A and B as A approaches B. That diagram indicates you're going from A to B. And so back in Cal 1 in that limit notation, that means you're approaching B with the negative superscript. It means coming from the left to the right has that negative superscript. So then you write this, the limit of C approaches B with that negative superscript, and then you go from A to C. Work this out. So once again, what's going to dictate the answer is whether or not that limit converges. That's the whole key here. Let's look at the next one. This is saying your discontinuity is at the lower value A. So it goes from A to B, where it closed at B. So discontinuity is at A. And so this time, to go from B to A, to approach A, you can only approach A from the right to the left, which makes that a positive superscript. So basically, in a nutshell, if the discontinuity is the upper value, it will have the minus limit. If it's at the lower value, it'll have the plus. Now, I didn't put the third case in here because I never asked that on an exam or anything, but suppose the discontinuity was in between the two, you would have to split it up as two integrals and then where it's separated by discontinuity. Unlike the example with the infinities, like I said earlier, from negative infinity to C and C to infinity, and I said you can choose any value you want for C. That's because it's continuous. This one you would have to split it off at the discontinuity. For example, without working it out, I'll just kind of go back up here and let me show you this one. Go way back up here. Yeah, this problem. To do this one, and that you would have to write this as -2 to 0, and then 0 to 3 as two separate problems, because 0 is where the discontinuity is. Yeah, so there is no choice in where to split those up. Now, let's try this out. So once again, I like to keep the integrals basic. And so the discontinuity is at 6. It's the upper. So the upper value, that means it will have the minus notation. So we go from 3 to C. And once again, like I said earlier with this lettering, heck, you could really use B here if you wanted to. You know, that's fine. I'm just using the C kind of as it's defined, but you could use B or A or whatever you wanted for any of them. And this integral is just in perfect arc sine form right here. Perfect. Let's see. So it's going to be arc sine of U over A. U is X. A is 6. So its limit as C approaches 6, negative arc sine of X over 6. So we have limit as C approaches it, 6 from the left, arc sine of C over 6. And then you plug 3 in there, so you have arc sine of 3 over 6, which is 1/2. Now with these limits, you think back to something back in Cal 1. Remember in Cal 1, you know, there was a rule said that if the left and the right limit equal the same value, then that means what I use the term regular limit, you know, without the superscript, would be the same value, and the vice versa is true. So what you want to do is just evaluate this as if it was 6 without the minus, and then if you get an answer, that meant the minus or plus limit would have to have been that same answer. So long story short, just don't worry about the minus. The notation's correct there and everything. But when we're evaluating, it's not important. So I plug 6 in there. I get 6 over 6. Arc sine of 1 is 90 degrees, pi over 2. And arc sine of 1/2 is 30 degrees, which is pi over 6. So we get pi over 2 minus pi over 6, and then so that converges to pi over 3. Excellent. Now here's another one that's just kind of a basic substitution problem. Yeah, it looks real close to that arc sine, doesn't it? But it's not when the x isn't squared. This one also has a discontinuity at the upper. So don't worry, we'll see discontinuity at the lower here shortly. It's at the upper because 8 makes that 0 on bottom. So I'm going to write this limit of c goes to 8 minus from 0 to c. And then I'm going to bring this up and call it 3, 8 minus x to the negative 1/2. And do a U-substitution. I'm going to let u equal 8 minus x. du is negative dx, so I do have to adjust for this negative. Now I'm going to show you a little thing here from Cal 1 that I did. I didn't actually write the negative, but I kind of have it sort of shown right up here. But anyway, let me show over here. I'm changing my limits of integration, so I never have to go back to x again. So u of c would be 8 minus c, and then u of 0 would be 8. Now there's a property of definite integrals that says if you put a negative in front of it, that reverses the limits of integration. So since I have this negative here and I want to get rid of that negative, all I have to do is go the other way and reverse the limits of integration, and that negative doesn't exist. So you see this negative right here, that's the reason why it's gone over here. That's why it's not shown at this part, because this bottom limit would have been converted to 8 and the upper one would have been 8 minus c. But you see I flipped them right here, and I flipped them strictly to get rid of the negative. Which, if you don't want to do that, that's perfectly fine. If you don't want to say, nah, I don't want to mess with that, okay, no problem. But I like to get rid of any extraneous negative signs. That decreases the probability of me making an error. All right, so I want to explain that carefully now. It's pretty straightforward. We're going to go power rule, antiderivative u to the negative 1/2. Just do the power rule. I'm not going to do that here, but it would be 2u to the 1/2. You plug in 8, and then you plug in 8 minus c. So we're going to need a limit where we plug the c in here. So the first one, I brought the 2 out with a 3, by the way, made that 6. And then that's just 8 to the 1/2 right here. Now, right here, so limit of c goes to 8 minus c to the 1/2. Plug in 8, you get 0 to the 1/2, which is the square root of 0, so that cancels. So that limit exists, so therefore we do have a converging answer here. So it converges 6 times the square root of 8, which would be fine with me, but as an answer, I don't care. But if you're checking answers or something like that, you might see it in a more simplified form. It's because the square root of 8 is the same thing as 2 square root of 2. So this is also equivalent to 12 square root of 2. But I would have no problem with 6 square root of 8 being your answer, because it's right. Now let's look at this one. So I'll go through this one a little bit faster, because this one has the punchline on this one's kind of interesting. It's almost the same as the last problem, except I changed that from 1/2 to the 3/2. And when I show this one in class, it's always kind of interesting, because a lot of students say that, yeah, when I got to the key part there, they said, yeah, that would have messed them up too. Okay, so everything's the same. I'm flipping the negative, all that good stuff. But I come down here, and now I have u to the negative 3/2 instead of u to the negative 1/2, which, using the power rule, actually gives me negative 2 to the negative 1/2. So I put 8 in here, which gives me 8 to the negative 1/2, which is 1 over the square root of 8. And then now, here's the interesting part. When you plug 8 in there, you're going to get 0. In the last problem, it was 0 to the positive 1/2. Square root of 0 is 0. Some people get the misconception that 0 to the anything is 0. That's true for 1. 1 to the anything is 1. But we've already learned that 0 to the 0 is indeterminate form, but in this case, it's not even that. 0 to the negative 1/2 is the same thing as 1 over 0 to the 1/2. So actually it's 1 over 0, which makes that undefined. So that part blows up, and that doesn't matter that we have a number here. If your limit blows up, the whole thing blows up. So that actually diverges. So that's kind of sneaky, isn't it? It's kind of like, wow, okay. Yeah, that would have probably caught a lot of people off guard. They would have just instinctively said, oh, I got a 0, so it makes it 0 raised to a power, that makes it 0. But no, that is not correct. This one would diverge. So I thought that was a very interesting contrast to the last example. Maple has infinity there. For some reason I've got a random logo here that I don't really need, but I'll just delete it so that way it doesn't look like there was supposed to be some information there, missing information or anything like that. So, all right, here's a basic partial fraction. Not likely to ask this either, but partial fractions are important. Anyway, in general. So I'm going to kind of go through this one pretty quick too here. So let's see. Yeah, the ones I kind of go through quicker are probably less likely to be on a test. But all right, easy decomposition, distinct linear, that's easy. So then you put 3 in there to get rid of b, so you get a times -1, so negative a equals 1, so a equals -1. Put in 4, gets rid of a, so you have 1b equals 1, so b equals 1. And then both these integrals are natural logs, so the integrals are easy. Now, as soon as we put the 6 in there, we're okay. 6 minus 4 is ln of 2. 6 minus 3 is ln of 3. But as soon as we plug, I wrote this as a fraction. You didn't have to. You could have left them separate, though. I don't know why I bothered to do that. Anyway, long story short, when you plug 4 into right here, you have the ln of 0, and that's essentially approaching negative infinity. That's why I wrote that. That's not important in the scheme of things, but ln of, as you go to ln, as the inside part gets closer to 0, you're approaching negative infinity. But anyway, that just blows it up. It means it's game over. It means it's diverges. Yeah, that shows positive infinity because actually you have 0 minus infinity, but not important. Well, actually, you don't have 0 minus infinity. Excuse me. You have a constant minus infinity, which would basically just be positive infinity. So I'm sorry, that's not 0 there, but I guess point being is that 2 minus infinity would be considered positive infinity. So that one diverges. Secant, this one really is just an integral rule right here. And it's a discontinuity at pi over 2. That's why this is improper. Secant of pi over 2 is undefined because it's 1 over cosine of pi over 2, which is 1 over 0. So this one you're really doing nothing more than just saying natural log of sec plus tan. And because it's upper makes that a minus. And then this one blows up real quick because, like I mentioned right here, pi over 2 is undefined for secant, and both secant and tangent. All it's got to do is be undefined for one of them, but the fact that it's for both is just a bonus. But anyway, that one diverges. Now, this kind of problem, this was a formula that we saw in 5.8. I think this, if I was to put this kind of problem on a test, I think that I would give you this formula, this particular one, just so you wouldn't be surprised with some formula you might weren't prepared for in your note sheet, expecting to have to use or something. So I like this problem, but it never hurts to be prepared and get as much stuff down there as you can. But yeah, I don't expect you to have to put the table of integrals on your personal note sheet there to But this one I think I would give this. But yeah, let's take a look at it. Or more likely, maybe I'd flip it around, make it 9 minus arc squared, and make it arc sine or something. So let's follow this formula. The discontinuity is at the lower. The 3 makes that 0. So that's a plus written right here. So it's c to 5 as limit as c goes to 3 from the right. 1 over square root of x squared minus 9, which we don't have to really integrate because we have the formula right here. If you had to do this problem manually, it would be by trig substitution. But like I said, I'm not going to make you do trig substitution on these kind of problems. That's going to be its own test questions. So it's not too bad having this formula. 5 and c, so you plug 5 in here. And 25 minus 9 is 6, square root of 16 is 4. So 5 plus 4 is 9. So you have ln of 9. So now it's all a matter of whether the limit's going to converge or not. So you see I replace that in there with c. I plug 3 in there. Okay, I like what I see so far. So that's going to be a 3 here. Plug in here. 3 squared minus 9. That's 0. Square root of 0 is 0. So you just have the 3 left here. So natural log of 9 minus natural log of 3, that's a good enough answer. But using properties of logs, that does equal the same thing as natural log of 3 by log properties. Now, I kind of, on the section 5.8 on the hyperbolic functions, I kind of skipped over this a little bit. I didn't worry too much about it. But these... I talked about the hyperbolic functions, but the inverse hyperbolic functions, which I think I might have mentioned a little bit there. The inverse hyperbolic functions all end up being these natural logs. So this particular integral is that arc sine h means hyperbolic arc sine. You don't have to know that. So, but Maple was programmed to answer them that way instead of this way right here. So that's fine. It wasn't using that formula. It was using it as hyperbolic sine. But obviously do not worry about that. But anyway, I just did a decimal evaluation in Maple for this. Just for your peace of mind to show you that did equal this. So that was a correct answer, but you're never responsible for that form. Now, how about this one? Now, this one looks kind of scary, but it's not. Absolutely not at all. It's just basic substitution. So I brought both these up, both the x's up. I have x to the negative 2, I have x to the negative 1, just so you can see that if I let u equal x to the negative 1, du is negative x to the negative 2 dx, and then there's how you get that part right there. So it works out perfectly as a u du substitution. Now we're off by a negative, so we'll have to adjust for that. And then I put b in here. So now I rewrote it back as a fraction, but b to the negative 1 would just be 1 over b. Now when you put 1 over pi in here, 1 over pi, that's saying right here, you're saying 1 over pi, which would just be pi. Now this one's interesting. I did not do like I said, that's why I'm saying that technique earlier was not mandatory. This one I did not use the flipping around of the limits, which, earlier when I had this negative, I used that property of definite integrals to flip it around. Well, look, I just left the negative here this time, which is fine. You do whatever you like. I think because I knew this negative was coming right here is the reason why I didn't do it, but you wouldn't be expected to see that. So you could have made that positive by flipping these two if you wanted to. So now I have 1 over b as the upper, pi is the lower, and then the antiderivative, not derivative, antiderivative of sine is negative cosine. Now the negatives take each other out. So we plug in cosine, put in 1 over b, and then put in pi directly. So cosine of pi will just be negative 1. So now the limit part's the $1 million question. So the way we look at this is infinity goes in for b. So we have 1 over infinity, which is 0. Therefore, cosine of 0 then is 1, so you have 1 right here. So it's 1 minus a minus 1, therefore we would say it converges to 2. And our friend Maple says it converges to 2. All right, let's take a look at one more. This is just a U-Substitution problem. I kind of picked this one because I wanted to see that don't make a mistake and think this is arc sine. You know, with that X on top, it's not arc sine. It's just substitution. So U is 25 minus X squared. Du would be negative 2X dx. So I have a negative 1/2 du. And then I didn't show the limits of integration where I changed them. But anyway, I did change them. But I can explain it to you real quick. So all I would have done is plug C right into here. And that gives me 25 minus C squared. And then I would have put 1 right in there for that X. So you have 25 minus 1 squared, which is 24. So I have the negative 1/2. And I did not reverse the limits of integration for this one either. Like I said, I didn't have to. I could have. I didn't. Oh, the minus notation, because the discontinuity is the upper value, 5. That's what makes it 0. So we have to approach it from the left to the right. So it makes it the minus. And now the antiderivative, u to the negative 1/2 du, is 2u to the 1/2. And I still have the negative 1/2. I did cancel the 2's. Yeah, I don't know why I didn't just use this negative and flip those around, but that's okay. No harm. Could have flipped them. So now we say the limit of c goes to 5 negative of 25 minus c squared, and then just put 24 into here, and you'll get the 24 to the 1/2 square root of 24. So now what happens with the limit? I put 5 in there. I get 25 minus 25, which is 0. But, you know, I showed you that example earlier, but this is 0 to the 1/2, so we're safe here. If that would have been a negative exponent there, this would have been undefined, and we would have had diverges. But 0 to the positive 1/2 is 0. Now, we have this negative in front. Maybe that's why that's probably a good, even though I didn't do it, I think I'm advocating a good reason for doing it, is why I should have not had that there, and I could have flipped them. And I wouldn't need all these brackets either. So the 0 minus square root of 24. So what you have is the negative of 0 minus root 24. So had I flipped them, I wouldn't have had this negative there, and it would have just been root 24 minus 0, which is root 24, or 2 square root of 6. I kind of think that's funny the way Maple did this, which is really weird to me, because I understand, you know, that you break down radicals when they can break, you know, when you can reduce the radical, like, so square root of 24 is 2 square root of 6. I mean, you can reduce the radical. But I don't see the point in breaking the square root of 6 down into the square root of 2 times the square root of 3. That makes no sense to me. But no harm, no foul, same answer. So, all right, that concludes this video on improper integrals.